So welcome to this is the Further Math Support Programme online revision session for OCR Statistics 1. And in this session we're going to be studying the binomial and the geometric distributions. So for each of them you need to be able to use the formulae for probability calculations for the binomial and the geometric. You also need to be able to use standard results to calculate for the binomial and for the geometric, and these are the standard notations that we use. You need to be able to work out the expectation, and you also need to work out the variance. Also, with the binomial, you need to be able to use correctly use cumulative binomial tables. So you're given quite a lot of information on a formula sheet as it stands. Okay, you're given for the binomial, you're given the probability function, so this is the equation for working out probabilities. And you're given that for the geometric as well. And you're also given for each of them the mean and the variance. And we don't need to worry about the probability generating functions. Okay, they're for a higher module. But they're the key things that we're looking for here. Okay, so January 2010 question 9. We're told that R and S are independent random variables and each of them have a geometric distribution with parameter P. And what we're asked to do is to find the probability of R equaling 1 and S equaling 1 in terms of P. Now the key word here is independent. So the probability of R equaling 1 and S equaling 1 is in fact just the probability of R equaling 1 and the probability of S equaling 1. Now we're told that each one of these, so R and S, can both be modelled as a geometric distribution with parameter P. So in each case, there is a formula. Let me just remind you of it. There's a formula here where it's P times by 1 minus P x to the minus 1. Okay, so remind you, probability that R is equal to a specific value is going to equal to P times by 1 minus P to the R minus 1. So here we're looking for R equals 1, so that's going to just be P times by 1 minus P to the power of 0. So that's going to give me P. And in fact, each one of those would be P. So we end up with P squared, which is quite nice. Part 2. So you only get 1 mark for that, but as I say, it's useful just to see where things come from. So for part 2, we've got to show that the probability of R equaling 3 and the probability of S equaling 3 is P squared Q to the 4, where Q is equal to 1 minus P. So again, just as a reminder, we can change the formula just to adapt that, so it's going to be P times Q to the R minus 1. So in each case we're going to get P Q squared, 3 minus 1, times P Q squared, which is 3 minus 1, which is going to give me the P squared Q to the 4 that we're looking for. So again, you only get 1 mark for that, but you do need to go through those steps. Part 3, we're then told to use the formula for the sum to infinity of a geometric series to show that a statement is true. Now, what you need to ensure with this is that you have learnt your core maths skills as well. Okay, so if we're going to use the formula for the sum to infinity, we do need to appreciate that we need to work out the common ratio. So let's think about what this is really saying. So the probability that R equals S is going to be the probability that R equals 1 and S equals 1, or the probability that R equals 2 and S equals 2, plus the probability of R equaling 3 and S equaling 3, and so on. Now we can appreciate that this is geometric. We worked this out. We were told that that was P squared. This one we worked out was P squared Q to the 4. And if you work this one out, it's going to be P squared Q squared. So we can see that we do have a geometric distribution where the common ratio is Q squared. We can also see that the first term is also equal to P squared. So as a reminder, the sum to infinity is going to equal A over 1 minus R, which is going to give me P squared divided by 1 minus Q squared. Okay, so we've actually done quite a lot of work so far. We've got 3 of the marks. Okay, we get 1 mark for working out the common ratio, we get 1 mark for using the formula, and we get an accuracy mark for getting this far. Now it's just a question of tidying this up. So Q is equal to 1 minus P, so Q squared is equal to 1 minus 2P plus P squared. Okay, just by squaring that out. So this becomes p squared divided by 1 minus 1 plus 2p plus minus p squared, just by substituting into this, which is going to give me p squared over 2p minus p squared. P is common on the bottom, so let's factorise it out. So that's p lots of 2 minus p, and then we can see that some things cancel and we get the correct answer. And I find it very satisfying when this happens. So you only get 2 marks really. You get 1 for attempting to use the fact that q is equal to 1 minus p, and then of course by getting to the correct step you get your final mark. Now please do not miss any steps. We show that questions, you need to show every single algebraic step that's available to make sure you're going to get all of the marks. So, January 2010, question 1. Andy makes repeated attempts to thread a needle. The number of attempts up to and including his first success is denoted by x. State 2 conditions necessary for x to have a geometric distribution. So these are very similar to the binomial, so you need to be a bit careful with these. So the attempts are independent. Okay, so in other words, the fact that he hasn't been able to thread it the first time is going to not affect his future attempts. And secondly, probability of threading is constant. Okay, there are 2 conditions in this context that we need to be aware of, and you're going to get 1 mark for each. Assuming that x has a geometric distribution, so now we're told that it's geometric, so this is your value of p, we're asked to find the probability that x is equal to 5. Okay, so again we've got the formula to do this. The formula is going to equal p q to the power of 4, so it's going to be 0.3 times by 0.7 to the power of 4, and if we calculate that through, that's going to give me 0.0720 to 3 significant figures. So again, you get 1 for using the correct formula, and then you get 1 for getting the right answer. We've then got to work out the probability that x is greater than 5. So there are a variety of ways of doing this really. The most sensible way in my brain is to realise that it's the same as this. So having more than 5 is 1 minus the probability of there being less than and equal to 5. So what we can do is we can do 1 minus. Now, everyone will have p in it, so it's going to be 0.3 times by 1 plus 0.7 plus 0.7 squared plus 0.7 cubed plus 0.7 to the power of 4. Okay, because really we've got p, q, pq squared, so we've got p, pq, pq squared, and so on. So this is the sort of calculating way of doing it. And if we work all of this out, that's going to give me 0.168. So you get 2 method marks. You get for this, you get 1 method mark for swapping it round, you get 1 method mark for calculating, and then an accuracy mark for getting the correct answer. There are other ways of doing this, if you've remembered aspects of the geometric progression, but it's not required. We can just calculate it through if you wish. We're then asked to suggest a reason why one of the conditions that we gave earlier might not be satisfied. And it's this idea of independence. Now, if you keep trying something, you're getting more practiced at it, you're getting better at it. So as a consequence, practice does improve. So practice improves chances of threading. So we could argue that they're not really independent. Okay? Or you could state that the probability isn't constant because it's increasing. They're sort of linked statements there. Okay? So you get 1 mark for stating what's happening. So practice improves chances of improving or threading, and then you get another one. So therefore, independence not likely. And that will give you your 2nd mark. Okay. So, June 2010, question 4. We're now moving on to a binomial. We've got a random variable w, and we're told that it's got a specific distribution, and we're asked to work out two probabilities. Now, these are not particularly difficult, so we just need to calculate them through. And the great thing is, for certain values, we can use the cumulative table. So p is a third, and we can see that a third is in fact one of the columns in my binomial cumulative table, and we're dealing with the situation where n is equal to 10. Now these are cumulative, so this value literally can just be looked up in the table. We look up 2 and it gives me the value straight away, so that's 0.2991. Now for part B, I'm going to show you two ways of doing this. So you can either use the tables by recognizing that the probability of getting a 2 is the same as less than or equal to 2 minus less than or equal to 1. So we could use the fact that it's going to be 0.2991 minus 0.1040, and that's going to give you a value of 0.195. That's absolutely fine. Or there's a perfectly good formula. So the formula goes like this: to get a specific binomial value, it's going to be n combination x, p to the power of x, q to the power of n minus x, again where q is equal to n minus r. So in this particular case, we've got the probability that w is equal to 2 is going to give me 10, choose 2, p, which is the value a third to the power of 2, times by 2/3 to the power of 8. And if you calculate that through, you're going to get the same value, which is quite handy. So 0.195. Okay, so 2 marks for this. You get 1 for choosing the method in either case, and then 1 in either method for getting the correct answer. So, June 2011, question 8. Anne, Bill, Chris and Deepak play a game with a fair cubical dice. Starting with Anne, they take turns in alphabetical order to throw the die. This process is repeated as many times as necessary until a player throws a 6. When this happens, the game stops and the player is the winner. So find the probability that Chris wins on his first throw. So for each player, doesn't matter if it's A, B, C or D, each player is following a geometric distribution because it's all about the first time that it happens, and it's going to be a geometric distribution with a probability of success of 1/6. So find the probability that Chris wins on his first throw. Well, that's simply just going to be the fact that Anne has to not win, and then Bill has to not win, and then Chris wins. Okay, so that's going to give me 25 over 216, and I'm happy to leave it like that. So just think carefully about the context of the question. So Deepak wins on his second throw. So let's think about what's got to happen. Anne's got to lose, Bill's got to lose, Chris has got to lose, Deepak has got to lose, then Anne, Bill, Chris have to lose again, and then Deepak has to win. Okay, so that's quite nice, and then you can calculate that through to give you 0.0465. So you get 3 marks for that, and again it's just about going through the process more than anything else. The probability that Anne gets a third throw, so that means everybody has to not win twice for that to happen, for her to get a third throw. So we're really doing the fact that everybody doesn't win twice, so that's going to be 5 to the 6 to the power of 8. So again, 1 mark for that, and 1 mark for calculating it, 0.233. And then I need a new slide for this one. And then for part 4, Bill throws the die exactly 3 times. Okay, so we've got to think about how this can happen. So either, let's think about this for a second, Anne throws it twice, Bill, Chris, Deepak, so that's to the power of 8, so that's 2 throws each that nobody wins. Then for Bill to throw again, lots of things can happen. So let's just base that as our first thing. We'll worry about the rest in a minute. So either Anne has to not win and then Bill does, or Anne doesn't win, Bill doesn't win, and then Chris does, or Anne doesn't win, Bill doesn't win, Chris doesn't win, Deepak then wins, or Anne doesn't win, Bill doesn't win, Chris doesn't win, Deepak doesn't win, and then Anne wins, because if Anne doesn't win, he's then going to get another game. So what we need to do is add all of those together and then multiply up by the 5 6 to the power of 8. Okay, so this is just about logically working your way through the process and making sure you're getting the correct answer. So yes, it is geometric, but it's geometric with a twist in this particular case. Okay, so you're going to get 3 marks. Basically, if I see what you printed here, what's written here, you're going to be getting 3 marks. Your final mark is clearly going to come from doing the calculation. And if you add all those together really, really carefully, again, 3 sig figs is the standard level that we use, we're going to get 0.100. Okay, so the next question. 30% of packets of Natural Crunch crisps contain a free gift. Jan buys 5 packets each week. Number of free gifts that Jan receives in a week is denoted by X, so your variable is stated. Name a suitable probability distribution which she should use to model it, giving values of parameters. State any assumptions necessary for it to be valid. So we're doing it a fixed number of times, and there is a fixed probability of occurring. So we can model X as a binomial distribution where we're doing it 5 times, and the probability of success is 0.3. So we've got ourselves 2 marks for this already. So we then need to state the reasons why we think it's binomial. So what are the assumptions? So the assumptions are that the probability of a gift is constant. It doesn't change. We also need to realize that the gifts in packets are independent. So the fact that you've got a gift in one packet doesn't affect the other. Okay, and they are the main conditions that we're dealing with the binomial. And again, you get a mark for each of those. So now let's assume, as it says, that we do actually have a binomial distribution, and we want, as we have in a previous question, find the probability of x being less than or equal to 2 and the probability that x is equal to 2. And these can be looked up in the tables again. So the first one, I haven't got the table this time, but the first one is going to give me a value of 0.8369. And then the second one, I'm going to use the formula. So the formula was 5 choose 2, p to the power of 2, q to the power of 3. And if we calculate that, it's going to give me a value of 0.3087. So you get 2 marks, one for the formula and one for the answer at the end. Find the probability that in the next 7 weeks there are exactly 3 weeks in which Jan receives exactly 2 gifts. So here we're talking about receiving 2 free gifts. So that is the probability that we're dealing with. So the probability of getting exactly 2 free gifts was 0.3087. We're now dealing with a 7-week period. So my advice is always redefine. So let y be the number of weeks in which Jan receives exactly 2 free gifts. Takes seconds to write, but it's really quite useful. So y now follows a binomial. We've got 7 weeks, and the probability of success is going to be 0.3087. And I want the probability that we're getting 3 weeks. Now, this probability is not going to exist in the tables, so we do have to calculate this. So it's going to be 7 choose 3, 0.3087 to the power of 3, 0.6913, that's 1 minus p, to the power of 4. Okay, and we're going to get a method mark for that. We're going to get a method mark for defining the distribution as well in terms of the probability of success. And then calculating this through gives me 0.235. And there's my final accuracy mark. So be aware that sometimes you may be asked to sort of redefine a distribution and do something slightly more different with it.